Swayam Prabha. Digital India. Educated India.
Hello, so welcome to this Astrochemistry course, and we are now in lecture 7. To give you a brief recap of where we were in the last class, here's a small recap. In lecture 6, we discussed what the interstellar medium was, and that it comprises of gas and dust. We also saw that the interstellar medium is highly inhomogeneous or non-homogeneous, and it has different regions. And we discussed about the various regions of the ISM. That is, for example, the molecular clouds, starting from the molecular clouds all the way to the warm ionized mediums and the hot ionized medium, right? Wherein, the temperatures ranged from approximately close to 0 Kelvin, 2 or 3 Kelvin or 5 Kelvin or 10 Kelvins to all the way up 10 to the power 6 or 10 to the power 7 Kelvin. Okay, so I gave you a qualitative description of the various regions of the ISM using the illustration of the regions of ISM found in our Milky Way galaxy. All right. On that note, we shall continue further in this lecture, and today we shall be looking into this very interesting idea of the various similarities and differences between the ISM and Earth. Okay, well, what's our objective? Our objective is to study astrochemistry, which is the chemistry of molecules and atoms happening in space, right? For that, we must have a thorough understanding of what's happening on Earth. Once we have our feet well grounded and have a thorough understanding of chemistry that's happening on Earth, our task to understand chemistry in space is going to be much easier. Therefore, this comparison between the chemistry happening on Earth and the ISM is critical to better appreciate the various facets of chemistry happening in space. Okay, now, before we actually discuss the ISM any further, let's come back to Earth. Okay, right? Let's come back to Earth, and let me ask you this very simple and important question. It is, imagine, like 1 centimeter cube of space right next to you, right? Now, the space can either be solid or gas, very unlikely to be liquid. I mean, liquid can be inside a solid, in a water bottle or something, right? Yeah, but we're not near any water body, right? So the space right next to you is either likely to be predominantly gaseous, that is, the air that is in this room, or it can also be solid, some table, chair, etc., wall, right? Now, if I ask you to calculate the number of molecules present in 1 centimeter cube of space right next to you, what will you do? Is the question clear? The task given to you is calculate the number of molecules in 1 centimeter cube of space right next to you. Clear enough, right? So what do? You just imagine some space, 1 centimeter cube, this much. And how many molecules are present in it? How would you do? Where would you begin with? What would be the starting point? Well, you understand that in solids, right? In solids, the symmetry plays a much more of an important role. This is from high school physics and chemistry, and also, your undergraduate education, whatever you've had until now, right? So you would think that in the solid state, to calculate this number, I would need the symmetry of the substance, and then I would need the density. I would need more data. But if I'm considering, the gaseous state, it's much easier for me to calculate. Why is it easier? Hint, think high school. It's because you've all been exposed to this idea called as the ideal gas law, right? We all know about the ideal gas equation. And what does it teach us? It tells us that PV equals RT. Right? We have been exposed to this equation, right from 9th class or 10th class, or maybe in high school, and definitely in college, correct? But how do we use this equation in the present scenario? What have I given to you? I've given you the volume, which is 1 centimeter cube, correct? Yeah, the volume is 1 centimeter cube. And what am I asking? I'm asking for the number of molecules. But note, what is this? This is the number of moles in this equation. Okay, so it would be nice to have a recap of what this equation means in case you don't understand what it is. Pressure is the pressure exerted by the molecules, right, as part of the gaseous sample. The volume is going to be the volume that's occupied, the given volume, that's 1 centimeter cube, and is the number of moles from which the number of molecules can be obtained. What is R? R is the universal gas constant, whose SI unit is what? Is something like 8.314 something. And what are the units? The units are going to be, PV is going to be what? Kilojoules or joules? Joules per mole per Kelvin. So this is R. And what's the temperature? It's room temperature, right? So, it's an air-conditioned room. So approximately we can assume that the temperature is going to be close enough to be 300 Kelvin, right? And what about the pressure? The pressure is, well, we are in Tirupati. The pressure is going to be V0, approximately 1 atmosphere, right? Very close to 1 atmosphere. Okay, right? We're not that far away from the sea level. Okay, although it's slightly elevated, not more than 200, 250 meters max. Okay, right? So the pressure is going to be 1 atmosphere. Okay, and of course, this is going to be, if you want the number of molecules, by Na. And what is the Na? You're correct, it's the Avogadro number. And what is the value? The calculated value is going to be something like this many numbers. It's a number, okay, right? So the Avogadro constant is like this huge number. Okay, right? With all this, can we actually calculate the number of molecules present in 1 centimeter cube? We can approximately calculate, because the ideal gas equation is itself only an approximation, correct, right? Strictly speaking, the gases right next to us, which is predominantly nitrogen, close to 80% hydrogen, nitrogen, oxygen, and then hydrogen, etc., rest of it, right? Now, they're all not strictly ideal gases, but that can be a very good starting approximation. So we can go ahead and use this equation. Let us use it. So before using it, well, what should we do? They're all in different units, right? We've taken this in Kelvin, we've taken this in atmosphere, this is in centimeter cube, this is in joule per mole per Kelvin. It's always a good habit to start using SI units uniformly. So let's convert the atmosphere into to SI units. The SI unit is going to be Pascal. So what is the order? Which is going to be approximately 10 to the power 5 pascals. Correct? There is a prefactor, some 1.03 or some number, but we don't care about the exact number, as I'll soon tell you why. Okay. And how many centimeters is a meter? The SI unit of length is meter, and for volume is meter cube. So this is going to be 1 centimeter is 10 to the power minus 2 meters. So there's a factor of 3 here. So this is going to be 10 to the power minus 6 meter cube. Correct? Okay. And then we have the Avogadro's constant. Everything else is set. So we can now use a uniform unit system to calculate the number of moles. So your Nm is given by pressure times volume times Avogadro number divided by RT, which is approximately, we need not worry about the exact prefactor. The exponent is what we majorly care about. Is going to be what? 10 to the power 5 times 10 to the power minus 6 times Avogadro. You take it to be 10 to the power 23 or 10 to 24, 10 to the power 23 divided by, now RT is what? Your R is 300 and R is 8 and T is 300. So 8 times 3 is roughly 2400, right? Again, it's of the order of thousands. So we can do this. Okay, we don't need to worry about the prefactors at all. And this number is going to be approximately what? 10 to the power 5 minus 6 plus 23 minus 3, which is approximately what? 23 plus 6 is 29, and 29 minus 8 is going to be 10 to the power 21, correct? It is roughly of the order of 23 plus 5 is 28, and 28 minus 6 is 22, 23 minus 3 is 19, yeah. So 10 to the power 19. Are we good, right? So it's of the order of 10 to the power 19. 23 minus 3 is 20, 20 minus 6 is 14, and 14 plus 5 is 19. Clear? So the number of molecules, right, in 1 centimeter cube of space right next to you is how much? It's approximately 10 to the power 19 or 10 to the power 20. So we thought that the space right next to us is tiny. It's tiny. It's just this much. But look at the number of molecules present here. It's 10 to the power 19, right? And what does this calculation tell you? Now this tells you that actually the Earth that we live in is very dense. Okay. Now based on this number, this particular number, right, 10 to the power 19, number of molecules in 1 centimeter cube space right next to us is 10 to the power 19, and the implication is that Earth is rather dense. What do I mean by dense? By dense I mean we have lots of particles right next to us. Okay, are we good? So in just this much of space, I want you to kind of have an intuitive feel. We are talking about a lot of molecules, and this specific thing, the number of molecules in 1 centimeter cube of space, right? This is actually called as the number density. So please make note. Okay, the number of molecules or number of particles. It can be molecules, it can be atoms, it can be elements, it can be anything. Okay, the number of species present. I'll just put it as particles more generally. Okay, so the number of particles present in 1 centimeter cube of space is what is called as the number density. And the number density on Earth is approximated to be what? Something like 10 to the power 19. Okay, let us now do the same exercise in the ISM. Okay, right? Now the next task could be, why are we doing it? Recollect what we're trying to do. We're trying to find the differences and similarities between Earth and the ISM. So we started with one metric, that is the number density, and we calculated the number density to be 10 to the power 19 on Earth. Now we shall move to the ISM. Okay, so what is our task now? Compute the number density in the ISM. As soon as I give you this task, what is the immediate question you should ask me? It is, in which region of ISM am I talking about, right? Because it was just in the last class that we discussed that the ISM has multiple regions. Okay, let us just do the calculation for the extreme regions. What are the extreme regions? One was the molecular cloud region, right? In the molecular cloud region, where temperature was roughly of the order of single digit kelvins, right? We can, let's take an upper bound of 10 Kelvin. And what about the other extreme? We're talking about, what was that called? I think that was called, not warm, hot ionized medium, correct? In the hot ionized medium, the temperature was as high as 10 to the power 6 Kelvin. Okay, so between 10 Kelvins and 10 to the power 6 Kelvin, we can calculate. How do we calculate? Well, let us use the same ideal gas equation. It's of course an approximation, but we can still use it, right? So again, using the same equation, PV equals nRT, right? And let's just substitute the temperatures towards the end. Okay. Now, what do we need to calculate? We need to calculate the number of species, right? So this is the number of moles here. So this is again going to be the same way we wrote the equation back when we calculated this number on Earth. Okay. But notice this. Notice this point. I'm just going to call this Nm sub s to indicate the number density is calculated in space. I'll just call it N sub s, make it even more simpler. Okay, that's it. Now, but again, the volume is given to you. So the volume is going to be something like 10 to the power minus 6 meter cube. The temperature, let's say, is like 10 Kelvin to begin with. And the Avogadro number we know is approximately 10 to the power 23, right? The gas constant is also, we can take it to be approximately 10 units, which is what we did, right? Which is like, it's 8 in SI, so close enough to 10, okay? It's approximately 10. And what do we need to calculate? We need to calculate this quantity. But hey, on Earth, we understood that the pressure was actually 1 atmosphere, correct? But what is the pressure in the interstellar medium? I never told you anything about it, correct? So what is the pressure in the interstellar medium? What would be your guess? If I were to ask you without knowing anything, just with the understanding that the interstellar medium is the vast, almost empty space between two stars, excluding the disk space, what do you think is going to be the pressure in the interstellar medium? High or low? Before coming to a number, let's try to discuss this problem qualitatively. High or low? Low pressure, right? Because it's almost empty. And what is pressure predominantly due to? Molecules, correct? So it's going to be low. Now comes the next question, how low? Well, I don't actually expect you to answer this question, okay, because I should give you that number, okay, right? In the cold regions, the pressure, of course, also, varies across the different regions of the ISM itself. And when the temperature is 10 Kelvin, the pressure can be approximately given as 10 to the power minus, let's say, if I'm correct, 10 to the power minus 22 to 10 to the power minus 24 atmosphere. Let's take an upper bound of 10 to the power minus 22 atm. Okay, right? So it's 10 to the power minus 22 atmosphere. What about in terms of Pascal? It's going to be 10 to the power minus 17 pascals. Right? I mean, using the very same discussion that we did for the thing on Earth. 1 atm is approximately 10 to the power 5 pascals. Okay. Now let us substitute all of these in this equation to figure out the number density at 10 Kelvin in the interstellar medium. So the number density is going to be what? It is going to be again PV Na over RT, right? And so here, this number is going to be 10 to the power minus 17, and the volume is 1 centimeter cube, which is 10 to the power 6. Sorry, 10 to the power minus 6 meter cube. And what about the Avogadro number? It's of the order of 10 to the power 23. And in the denominator, we have the temperature is 10 Kelvin, and R is also of the order of 10. So this is going to be 10 square. Now, what is this number going to be? 10 to the power minus 23, right? Are we all clear about what we're discussing, right? Yeah, pressure is going to be like this many pascals. This is the volume element. This is the number of the Avogadro constant, and this is going to be the RT factor. So this is going to be 10 to the power minus 23 plus 23 minus 2. What is this going to be? Approximately 10 to the power minus 2. Correct? So if we choose the value of pressure to be 10 to the power minus 17 Pascal, right? What do we get to be the number density? 10 to the power minus 2. Can you imagine? Can you imagine, right? Can you compare the sparsity? Can you compare the sparsity that is occurring in the ISM with respect to what's happening on Earth? What was the number density that we calculated on Earth? on, so this is number density in space. I'm just calling the number density on Earth to be like nm, which is the symbol we used earlier, 10 to the power plus 19. So you can imagine, right? You can imagine how sparse, imagine how sparse the ISM is actually, right? Please take it into your brains, okay? Please get into this idea that the ISM is actually exceptionally sparse. Okay. In fact, I'll give you a fact, okay? I had given you some value of the pressure, right? Now, even though from this particular calculation, the number density we calculated was 10 to the power minus 2, it turns out that in the densest regions of the ISM, that is in the molecular clouds, note, in the densest regions of the ISM, what are they likely to be? Based on our previous lecture, are you able to connect it with this one? The molecular clouds, right? The molecular clouds, right? The number density is actually, slightly better than this 10 to the power minus 2. It can be as high as 10 to the power 6, in fact. It goes up. Can go up to 10 to the power 6. Please note this point, okay? So we made this approximation of ideal gas, and we took an approximate value of 10 to the power minus 22 Pascal for the pressure, right? Under that condition, we obtained the number density to be 10 to the power minus 2. All right. However, the pressure can be slightly higher, and the number density can actually go as high as 10 to the power 6. Please take note of this point, okay? Right? Now, I keep this part intact, okay? I keep this part intact. Now, this was for 10 Kelvin. What about 10 to the power 6 Kelvin? Well, the denominator here is going to be, instead of 10 square here, it is going to be 10 times 10 to the power 6, which is 10 to the power 7 overall, right? And so, it's going to be minus 23 plus 23 and 10 to the power minus 7. So, from this calculation, the number density that you get at very high temperature is going to be what? Even less. It's going to be even less. Okay, so we are clear about that part. So we have looked into this extreme, which we calculated to be 10 to the power minus 2, the number density. And here, the number density is approximately 10 to the power minus 7. I don't worry about the exact magnitude of these numbers, okay, because we made several approximations. First up, the ideal gas equation itself, okay. And the next one is that I gave you an approximate value of the pressure, okay. So in the extremely dense regions, the situation is better, but in comparison with Earth, it is still 10 to the power 13 times more dilute. Please note this point, okay, right? The ISM, even the densest region of the ISM, I want to highlight this here, okay? Even the densest region of the ISM is very dilute with respect to, where we live. It's dilute, okay, right? So even the densest region of the ISM, which is the molecular cloud region, is still exceptionally dilute and sparse with respect to Earth. Please make this point clear, okay? It is the idea that we roughly had an estimate for the number density at 10 Kelvin and also 10 to the power 6 Kelvin, right? Now, in fact, at temperatures as high as 10 to the power 6 Kelvin, many times, okay, I must make it clear that the ideal gas equation, right, is not even valid for the most part. Because the pressure in that region, see, even when we use the value of 10 to the power, minus 22 atm, the pressure, the number density was 10 to the power minus 7 or 8, right? But what is this pressure? The pressure in this equation is due to the molecule. This is what is called as the thermal pressure. Now, at very high temperatures, okay, at extremely high temperatures, the idea of what is called as molecular equilibrium, we'll discuss this more when we discuss thermodynamics and thermochemistry in the context of astrochemistry, okay. Now, This is the thermal pressure, which is due to the pressure exerted by the molecules of the gas sample, or the molecules of the molecules present in the gaseous state. But this thermal pressure, P is almost zero at temperatures as high as 10 to the power 6 Kelvin. Okay, I'll make it clear. P thermal, okay, the P thermal, P capital T, right? PT is almost zero. So therefore, this ideal gas equation, itself is not so valid at very high temperatures, because this equation assumes that the pressure is exerted actually by the molecules. You get it, right? So the pressure, this equation is valid only when the pressure that is being exerted is by the molecules. So the pressure, at such very high temperature, right, is actually arising due to various magnetic and gravitational turbulences. P due to magnetic and gravitational turbulence is much greater than the P thermal itself. So please note this point. So whenever you want to use the ideal gas equation, especially at such very high temperatures, it's pretty tricky. Okay. In fact, even at low temperatures, it was still an approximation, but still a better approximation in the ISM. In the tutorials, whenever we discuss it, in fact, I will focus on this particular aspect, when the ideal gas is valid under interstellar conditions and when it is not. You may be confused at this stage slightly. After all, on Earth, we keep saying that the ideal gas is more valid at high temperatures, right? At high temperatures and very low pressures. But I'm saying that at very high temperatures, well, the thermal pressure is not even existent. Okay, so I will clarify this in the tutorials if you're confused as to why this equation is not valid. But what is the bottom line? The one-line summary as to why this equation is very unlikely to be valid at very high temperatures in the ISM is because the pressure, in this equation corresponds to the thermal pressure, which is due to the molecules of the gas. But there are very few molecules present at such very high temperature where almost nothing exists. Okay, the pressure is predominantly due to magnetic and gravitational turbulence. Okay, so please make note of this point, right? Yeah. So now, having computed the number density and having illustrated to you the difference between the ISM and Earth in terms of number density, I will end this class by giving you a small tabulation of the number densities in the various regions of the ISM. Okay, I just told you that at 10 to the power 6 Kelvin, right? It's extremely sparse. At 10 Kelvin also it is sparse, but not so much. And in the molecular clouds, the number can go as high as 10 to the power 6. Okay, so I will just tabulate it, take it again for granted. The exact calculations, some of which we shall again revisit in the tutorials. So in the molecular cloud, so this is the region and this is the number density. I'm going to call it number density in space. So in the molecular clouds, as we just saw, the number density can be as high as 10 to the power 6. This is per centimeter cube. Okay. What is the next region? The next region is the cold neutral mediums. So in the last class, I told you, right? Cold neutral mediums. And what is the number density going to be here? Is of the order of, it's already going to be dropping to around 100. We're talking about a 10 to the power 4 magnitude drop. Okay. And what is the next region? The next region is the warm neutral medium. Again, I'm using abbreviations in the last class. Okay. And how would the number density vary? Well, it would be less than 1. We're not even talking about a whole number here. And what is the next region? It's the warm neutral medium and the warm ionized medium. Warm ionized medium. And what would be the number density expected? Also less than 1. It's also a good habit to tabulate the temperature. The temperature here is approximately 10 Kelvin. Here is of the order of hundreds of Kelvin. And here is of the order of thousands of Kelvin. And here also the order of, thousands of Kelvin, right? Close to 10,000s of Kelvin, right? Thousands or 10,000s of Kelvin. I would call this 10 to the power 3 with some prefactor. Okay. And what is the next region? The next region is the H2 region. Here also the temperature is of the order of 10 to the power 4 Kelvin. But notice that in the H2 region alone, the number density can be as high as 10 square. So please make note of this alone, okay? The reason for this, we shall elaborate in the tutorials. And lastly, what's the last region? It's the hot ionized medium. Temperature, roughly 10 to the power 6 Kelvin. And what is the number density? Well, as you would expect, is even less than 10 to the power minus 1. Okay, right? So this is how sparse the interstellar medium could be. On that note, we end this lecture, and in the next lecture, we shall see more interesting similarities and differences between the ISM and Earth. Thank you.